Thank you. I don't need the mic because I'm loud. When the Citus guys came to me with the PG shard thing, I immediately, of course, started thinking, because I do all of this work supporting companies that have web applications, I started thinking, hey, distributed, particularly because we're coming right around for 9.4, distributed database. And I was like, hey, I want to do a test where we give a workout to both PG shard and to the new JSON-B indexing functionality. So what I did here, I did this in December to help test out, the PostgreSQL, the release candidate. And I actually just reset this up this week. So what we have here is we have a bunch of Amazon instances. We've got a master running on a memory optimized extra large, and then we have 8 shards instances running on memory optimized large instances on Amazon. The idea here was, as you would want to with sharding, to size them so that each shard's portion of the database would fit in memory. Because after all, we're talking Amazon, and even if you're using local instance storage performance is just really not so good compared to own hardware. So you really want to keep things in memory. So set all of those up. I actually already have one blog post out hold on a minute, in December on Database Soup, which explains how I set them up. So if you want to take a look at that. So you can check that out later. I'll be putting other stuff now about the tests I've been doing lately on my blog, so you can see those. But that's the shard setup. Now, let's look at a few things here. So, in order to test this out, I created this sort of fake data set called psocial, which is just a big sort of blobby JSON data set for supposedly a kind of social application. So what we've got here is we've given up on the relational model, and we have this one table database, which consists of an ID, which is actually a UUID-ish thing, an email, and a profile, which is a big JSON-B block. And if you actually, I can't, displaying that in that format doesn't work quite so well, so let's actually look at it on the screen. And look at the JSON-B blob. What we have is some personal information. We've got a repetition of the ID, a hashed version of the password, repetition of the email that we've got in another column, a bunch of filler for stuff. And then for some people's profiles, we have a bunch of groups that they belong to. And, what group they belong to, whether or not they're an admin for that group, and how long they've been a member. And then a bunch of other personal information. For other people, a bunch of personal information, and we might have, for example, say, multiple addresses that they've had. Part of this was I really wanted to generate some inconsistent, jagged data the way that you would have in an application that stores stuff in a JSON-B database that has changed over in a JSON-B, where the application has changed over time. And so I did a lot of sort of generating of data to set that up. And I'll be I put some of that up on GitHub already. I'll put more of it up soon when I actually have some useful tests to come out of this. So, now, part of the idea of this was to test PG shard. So, this members table that I just showed you, is empty. This is the head node, and there's actually no data being stored on the head node. That'll take a second. One of the things that has not been implemented in PG Shard yet because of some underlying dependency issues in core Postgres is pushing down aggregates to the individual nodes. So this actual select count star is going to be slow, relatively speaking. But we've got a little over 10 million individual profiles in there. Those 10 million individual profiles add up to about 40 gigabytes of data. Obviously, with a real database that size, you could actually just get a larger Amazon instance, put it all in one instance. But imagine if you had 400 gigabytes of data and you were still committed to hosting on Amazon. At that point, you can't get a large enough instance to cache that 400 gigabytes in memory. And so part of the idea here was to shard it out so we can make sure it's all going to be cached in memory. I'll show you one more thing here. So, where is all of our sharded stuff? So, one of the things that PG Shard keeps, and the guys will be explaining this more, but here I'm giving you the hands-on demo, is you have metadata being stored in tables in this special PGS distribution metadata schema that gets installed as part of the PG Shard extension. If you actually want to, here's our PG Shard extension, version 1.0. I actually, by the way, this is actually the development version, so it's not really, strictly speaking, version 1.0. So we've got several metadata tables, one of which is partition, and partition table just holds one record per sharded table. So here's our OID, the sharded table. Here's the partition method, which is hash, which is all that's supported currently. But in the future, guys plan to support other forms of partitioning. So we've got a field for that, and what the key column is. Now, it's much more interesting to actually look at, for example, a list of shards here. So the list of shards here, we've got the shard ID, what relation we're talking about, whether it's a storage shard, and then this is a range over the hash values for that shard. And this is using Postgres internal hash function. So we're just getting a 4-byte integer out of it. And then we map the entire potential domain space and divided everything out into 16 shards. And the reason why I picked 16 shards in this particular case is I'm using R3 large instances which have 2 cores. And so I wanted to have, anytime I did a query that got pushed out to all shards, I wanted to have exactly 2 processors busy, 2 cores busy per machine. And so that was the reason for doing 16 shards. Something to consider. Obviously, in a real sharding situation, you would actually over-allocate shards so that you could split later on, and add more nodes. Now, the other thing that PG Shard does for you is that it actually does redundancy. It does some round-robin redundancy. So if you look at the shard placement table, you can see that each shard is actually written to 2 locations. So we have duplicates of shards. So I can entirely lose one of those Amazon instances without losing any data. So let's do some queries. Oops. Let's not scroll a whole bunch. So I mean, here's the obvious scrolling too much. Here's the obvious thing, which is to just do. Well, let's do this sideways, hey? Which is to just do a lookup by ID. And that's super fast because we can map, because that ID is already mapped to the hash map for PG Shard. And so it's as fast as if we had all of the data locally and fit it in memory, and fit in memory, except for a tiny bit of network lag. Now, we can also look things up by non-hash indexes. Okay. Let's put some timing on. It's funny, when I was selecting that, oh, it is a little bit slow. So that's 23 milliseconds. Oh. Of course, Amazon. A little bit of variance in the amount of response time from the network. When I was testing this earlier, it was a little bit more clear, where the lookup by the hash key was about, 80% faster than the lookup by the non-indexed hash key, because this is actually going by a non-hashed index, and it's actually hitting all 8 shards in order to, well, all 16 shards across 8 nodes, in order to look up that one account by email address. So the fun part about this, though, obviously, is pushing down some of these JSON queries. So again, for members here, we've got this members thing, and I put a GIN index on the profile, and this is the big feature for 9.4 in terms of non-relational data, is that you can now, in our earlier version of JSON, you could put indexes on specific keys, but you couldn't generally index everything in the column. And now you can use the GIN index, and it allows you to generically index every single key in the column, even nested keys, and do index lookups on them. So there's an obvious thing, like for example, I'll say, okay, let's go ahead and look up how many people do I have in the database who are in SFPUG? So there we go. So 206,000. So SFPUG's grown a little bit since we started it out. So we got that. Okay, well that's way too many. So let's look up how many libertarians do we have who belong to SFPUG. So 8,000 libertarians who belong to SFPUG. How many, let's compare that, how many libertarians do we have who are also Trekkies? So we have more libertarian Trekkies than we have libertarian Postgres people. I don't know what that tells us. So let's narrow this down a little bit. Let me see how many libertarian Trekkies we have in the Boy Scouts. And that's none.
So is this going across every shard?
It is going across every shard, yeah. What it's doing is it's pushing down the query to every single shard. And unfortunately, one of the unimplemented things, one of the things that's not implemented is explain. So I can't actually show you an explain plan that shows you the push down. But this portion of the query is going to push down to every shard. It's hitting the GIN index in every shard. It is returning a response up to the front end. And then doing the count across that response. For that reason, you'll notice that the queries that return few rows are substantially faster because they're not sending as much data across the network. Yeah?
Do you have any idea of how fast this would be on hard disk, one node?
On one node with multiple shards? Haven't tried it.
Just one day. This is normal.
Oh, you mean this data set on one machine, on one hardware?
I guess I should just.
It would probably be faster, actually. So the question was, how fast would this be if I took all 10 plus million and threw it on decent hardware, on my own decent hardware? And I would say it would actually probably be faster. When you start looking at something like this is when you start looking at sharding, period, whether it's PD sharding or otherwise, is when your data is really too large to reasonably do on one machine. If your data is small enough that you can affordably buy enough RAM to cache that database or fast enough storage to read that database in a few seconds, then do that. But particularly if you have adopted an AWS or other public cloud-based hosting environment, the ceiling on how big the database can be before you're paying the penalty for all of that network-based storage is fairly low.
One thing with machines, it can be faster the more machines you start because you actually use more.
No, I understand that. I was just kind of getting like what the performance part.
Yeah. Yeah, until we get parallel query until we get parallel query in core Postgres, this can also be a hack to get around the lack of parallel query in core Postgres.
So does this query the shards in parallel?
Yes, it does.
What happens if
Synchronous
we're...
IO.
Okay, no, I'll say all my questions so many times.
Okay, so now we're going to look at how many libertarian Trekkies do we have who also belong to MUFON, the Mutual UFO Network. It's a fair number. And then let's start looking at some other fields. Like, for example, hey, let's take these libertarian Trekkies who belong to MUFON and see how many of them were active in the last year. Well, that's none. And now we're back to doing that again. Hold on.
Maybe I have to push it back.
Yeah. I don't know, I did this before and it just didn't register until I unplugged and replugged it in like 5 or 6 times.
Shot me.
Yep.
Dios plus. I'm trying getting another operating system.
That's not the operating system problem. It just, in the middle of the presentation, it just stopped noticing it was there. And like I said, as far as the laptop is concerned, it's attached to the display. But the display is not registering that there's a laptop attached to it. Yeah, I didn't do anything. I did this before, actually, and I wasn't even at the podium. So.
Would you like to do food now? Pretty much ready.
Yeah, I'm the, okay, I was going to do a few more demos of queries, but I guess that's not going to happen.
Possibly when we get a fix.
There was only a couple more things, so it's just really not going to be worth it. Yeah. Okay. At this point, yeah, let's just go ahead and write for. we'll break for food. All right?
I guess you have a question.
I can't do anything. So, the, because I would be wanting to show stuff in the workshop. I can't show stuff. The, okay. Okay. Okay, so we're breaking for food.